In this video, I'm going to be solving another example from the second law of motion worksheet that was given. And so we'll go through to solve this one, which is a slightly different problem, but still the same general idea. So first off, again, we know this is one of those questions based on the second law of motion, so we'll write out our equation again. And it is that the net force is equal to the object's mass times its acceleration. I'll go ahead and write out the other two forms like I did in the previous video. So net force divided by mass is equal to acceleration. And the third form, net force divided by acceleration, gives us mass. So as a reminder, these equations are all equivalent to each other. They can be converted from one to the other. I'm just writing them out this way for your convenience. So now that we have the equations that we can potentially work with, we should look at what we're asked for. In this case, it is the train's mass. Because of that, we should be looking for the equation that is solved for the mass. In other words, where mass is found alone on one side of the equation. The one that does this is this equation, the one on the right. And so that's the one that's going to be the best for us to work with in this problem. Now that we know the equation that we're working with, we can go ahead and start plugging in the values. We would need to find the net force and the acceleration. And we can see that we have the force shown here. It's negative 3.8 times 10 to the 6th newtons. So a lot of force going on here, much bigger than other values you may have seen. That goes on top according to our formula. And the acceleration should go on bottom, and we can see that is here. Acceleration negative 0.33 meters per second squared. And this will be equal to the mass. Like we did before, I'm going to switch around the units a little bit. So this again goes back to our definition of what the Newton is. The Newton, we said, was defined as being kilogram times meter per second squared. Can then keep our acceleration as is. And again, since we're just substituting in equal values, we should say that is equal to our mass. This is going to come out slightly differently from the other one, but have the same kind of thing happening. We have meters per second squared on top and on the bottom. So when we cancel that out, we're just left with kilograms here, which tells us that we're going to end up with a mass in kilograms, which is good because mass generally is measured in kilograms. That is our SI unit for mass. We can also see that we have negative values on top and bottom. When we divide those, we should end up with a positive mass. Also a good sign because we should expect masses always to be positive. When we do this division here, we will end up with a value that is 1.15 times 10 to the 7th kilograms. And that equals our mass. So this should be the mass for this problem. We see that's a very large mass, but that should make sense considering this is a freight train, so it should have a very large mass. That should take us through this problem, and I will include one last example to show one last application of the second law to these new problems.